Hopefully people will start trickling in. Okay, good afternoon, everyone. I know we've got some more people joining us. They'll start trickling in. I'm sure people are coming from other meetings, etc. So we'll just wait a minute or so for them to start coming in. Let's see, numbers are increasing. I think in the interest of time, though, we'll kick off. So yeah, firstly, a big thank you to everyone who's joined so far. As I said, we'll get more people joining as we go through. For those of you who don't know me, I'm Alex Oliver. I'm the partnerships lead for the REWIRE Innovation and Knowledge Centre, and I'm delighted today to be joined by our two speakers, who I'll introduce in a second, and they'll be presenting on some really interesting work around scanning probe microscopy and atomic force microscopy for wide bandgap semiconductors. So our first speaker is Dr. Peter de Wolf, who is Senior Director of AFM Technology and Application Development at Bruker Nano Surfaces. He leads the team there of their development and application scientists, where they're focused on the development of novel AFM techniques, some of which he'll discuss today. He holds a PhD in electronics engineering from the University of Leuven in Belgium and IMEC. On the topic of nanoscale 2D carrier profiling in semiconductors, and has developed several AFM methods for nanoscale electrical characterization. He is author and co-author of over 40 publications related to property characterization using AFM, and owns several AFM patents. And our second speaker today is Chen Chen, who is a PhD student supervised by Professor Rachel Oliver in the Department of Materials Science and Metallurgy at the University of Cambridge. His research focuses on developing characterization techniques for nitride-based high electron mobility transistors structures, or HEMTs, especially using scanning capacitance microscopy. And his aim is to understand the structure property relationship of these structures. He was awarded the Best Student Award for his presentation at the 14th International Conference on Nitride Semiconductors in 2023. And he also holds a Master's of Science from Ulm University in Germany, and a Bachelor of Engineering degree from East China University of Science and Technology in China. So without further ado, I will hand over to Peter to present his slides. Just to say, if you do have any questions or comments that you want to add to or pose to the speakers today, feel free to add those to the chat or the Q&A functions. Those should both be enabled. We'll come to the Q&A section at the end of the presentations today. So yeah, I will hand over to Peter to start his presentation.
Thanks, Oliver. Good afternoon, everybody. Thank you for joining. And thanks to the organizers to give me an opportunity to talk in this webinar and talk in partnership with Dr. Chen, who I had the pleasure to work with for a couple of times on some very interesting samples that he will share. I think you can view my section as a good introduction to his work, which will be a little bit more advanced and special, focusing on a specific case study. I will talk to you about how atomic force microscopy can be used on wide bandgap semiconductors, and in particular for electrical characterization. If you're not familiar with AFM, just one slide on its principle. In AFM, we use a very sharp tip, which is typically sharp down to the single nanometer, that will raster scan the sample. And while doing that, we will measure the interactions between that tip and the sample, and also control them to typically operate at constant low forces, enabling us to resolve 3D topography structures of those samples. Relatively simple and straightforward mechanism, but actually quite powerful as we are using a probe that it can be in contact with the sample. That probe also will allow us to do specific property measurements, whether they are mechanical or electrical, with that same resolution. I like to use this map, which sort of shows the application range of AFM and its derivative methods in terms of spatial frequencies. And we go, for example, down to the angstrom level, up to typically around 100 micron, as well as the height range. We can look at very smooth surfaces, atomic lattices, crystal surfaces, as we often actually have in semiconductors, to below an angstrom up to about 10 micron. There's two examples here. This is actually an atomic lattice on the calcite, 32 nanometer scan. And this is on the other range, range of the spectrum. It's a 60 by 60 micron large area scan. We consider this large, looking at a step that is about 10 micron in height. Anything in between can typically be covered, whether your sample is hard, like we often have in semiconductors, or soft, like in biological applications or so. Now, switching to the semiconductor applications, the wide bandgap materials. I have a few here that I selected, mostly silicon carbide and gallium nitride on silicon carbide, where we look at some of that topographic capability that the AFM offers. In the first image here, we have a surface that has terraces, and it is actually very smooth. The roughness is below 1 nanometer, is actually below 1 angstrom. The height variation is below 1 nanometer. Gives you a feel of what type of height resolution one can resolve. Second one is a similar application. Now we're looking actually at those steps. Those steps have about 3 angstrom or 300 picometer height on a 6-gauge silicon carbide substrate. A common application is to look at gallium nitride, whether it's gallium nitride on silicon carbide or just gallium nitride, and the dislocations formed in that gallium nitride, as well as the terraces. And things like dislocation densities can be a very important quality factor for the substrates that we'll be trying to use for creating devices. So here's a large area scan, large in terms of AFM, 20 by 20 micron, resolving the large area surface morphology. But then if we zoom in, and this is now a digital zoom, because these images can be up to a couple of thousands of pixels by a couple of thousands of pixels. So it can be very data rich, and we can see individual screw dislocations here, as well as some other defects there that could be of interest to qualify the substrate. Typical roughness application. Another application for topography, or maybe more of an industrial one, actually is to go and use it for critical dimension metrology, and often for some type of quality control. The application I selected here is patterned sapphire substrate, or PSS substrate, basically the substrate the treatment that will be used to create optical devices like LED devices or so. So the process creates these micron-scaled domes, and the shape of these domes is very important for the performance of the devices that will be made out of them. And shape is determined by things like width, height, angle on the left side, angle on the right side, something we call the turn height. There's a little kink in that profile that we like to resolve and measure the height at which that occurs. The top, the feature, is that flat or is it spiked? That's an important information, and then also potential asymmetry in either the X or the Y direction. So that type of information is truly 3D information that is of interest and relevant to the devices that will be made out of it. And AFM is perfectly suited to do that type of measurements. And I show a couple of examples here on different PSS structures where there's, for example, that kink height here. There's a flat top. There's a clear asymmetry in one direction, but not in the other direction. Those are important things to know. Alternative to AFM is often the SCM, but SCM for this type of application, for example, is destructive, as we need to make a cross section and then do the metrology on the cross-sectional view. AFM is non-destructive and therefore better suited for this particular application. So I mentioned that we use a very sharp tip that interacts with the sample, can be in contact with the sample, and this enables us to also do specific property, physical property measurements. I like to group them together in different categories. There's a couple of them that are electrical or electromagnetic, and whether it's conductivity, magnetic field, electric fields, and a couple of other ones. And typically, if there is an electrical property that we are interested in measuring, typically there is a way to do that with AFM. And most of today's webinar properties are accessible as well. Thermal properties, mechanical properties, and even chemical identification. For example, if the samples are contaminated, identify how large that contaminant is, but then also what is that contaminant? Is it an organic contaminant? What is the exact composition of the contaminant? There's modes that exist for that. I don't go into all of these. I will not go in mechanical and chemical today, but this is definitely within capabilities of AFM, and I'll be happy to talk about it if somebody has a question or so. Properties translate into operating modes and lots of acronyms. I list some of the AFM modes, and I probably missed a lot here. There's a lot of acronyms in AFM. It can typically get confusing. I like to focus on the property, and then depending on things like, is my sample soft? Is it hard? What type of quantification do I want to obtain? One or the other AFM mode, as we refer to, will be the preferred choice. I won't go too much into the detail of that because it quickly gets on a long discussion. But I will go into some examples for the large bandgap semiconductors. So first, this is a published result from a while ago, but it's a nice illustration of the first property, the conductivity measurement. So here again, we have one of these gallium nitride surfaces with the relatively large dislocations. And we're interested in measuring the conductivity of that substrate, and in particular, the behavior around the dislocations. And we can see here, when we measure at the same time as the topography, conductivity by applying a DC voltage and measuring current through current amplifier, we can observe that the current at these dislocations is considerably higher than at the substrate, so indicating potential leakage paths and other issues. Similar to conductivity, resistance typically is considered as a different property, mainly for one reason, is that resistance, when we go to semiconductors, will vary over many orders of magnitudes, depending on the carrier level or the dopant level within that semiconductor. This is here a cross-section device. I don't show the topography because it's pretty boring. It's not showing anything. The sample is prepared by cleaving. But the resistance map shows the multi-layer structure of that sample. And the colors here represent to the resistance for the log or resistance between the tip and the sample. And that resistance directly scales with the carrier concentration, or reverse scales with the carrier concentration of the sample. And you can see if we make a cross section through this, because these are always nice color images, but what is really of interest are the values. So we make cross sections through that, and we can see that the resistance varies from, this is a logarithmic scale, from about below 6 to well above 11. So we have like 5-6 orders of magnitude of resistance change that corresponds to carrier concentration changes from typically 1E15 to 1E21 type of range. And then, of course, depending on the material, gallium nitride, aluminum gallium nitride, and others, there can also be a variation, and that's what we will measure with pretty much close to the single nanometer resolution. I have two more examples of that. Now it's actually of indium phosphide, so it's more of a small bandgap semiconductor, but similar technique. I like these examples because first they illustrate spatial resolution. Some of these layers here are only a few nanometer in size and they can be resolved. These are again cross-section devices. And second, in terms of carrier concentration sensitivity, this is a test structure where there's multi-layers, and every second layer, the concentration changes by a little bit. Like these last two steps here, for example, the N-type doped is 1E17 and 1.7 E17. So that difference, which is relatively small, can easily be detected by this technique. Same on the P-type concentration levels. Gives you a feel about resolution and concentration sensitivity. I'll go through a few more of these property measurements. The next one is capacitance, and this is really also the topic that then Chen will cover in more detail in his presentation. In scanning capacitance, we will measure, rather than the resistance, we will measure the capacitance between the tip and the sample while applying a voltage between those. Typically, we will be applying an AC voltage. The AC voltage allows us to accumulate and deplete the carriers below the tip in the semiconductor, which gives us a capacitance variation. It actually gives us two signals. One is we refer to as capacitance DC-dV phase, and one is DC-dV amplitude. The D referring to, it's a derivative because we're applying an AC voltage, so we can look at differentials. The phase signal will be representative of the dopant type or carrier type, and typically we'll take two values. It's maybe best shown in this higher resolution scan here. There's the N type is dark, the P type is bright, and then if it's a bit noisy in between, that typically means that it's hard for the instrument to detect whether it's N type or P type, because either the carrier concentration is very low or too high, that it's hard to really detect if it's a semiconductor or not. But like here, N-type, P-type region are clearly visible, the top region, as well as again, P-type, that's clearly visible. And the second image, the amplitude image, is sort of an intensity image, where typically higher capacitance derivative corresponds to lower concentrations. Typically is used for things like where is the PM junction nicely profile that with resolution on the order of like 10 nanometer, as well as look at diffusion effects. Like this is a double diffused implant, so we have one here and a second one there, and look at the diffusion, maybe lateral and vertical or in depth, how they differ, and maybe result in specific shades that are not intended to be there. Here I actually do show the topography, and as mentioned, cross-section devices won't show much topography variation. If we apply this on top surfaces, like here on gallium nitride, processed gallium nitride nanowires, there's a couple of nanowires here that stick out, but actually this is a field of adjacent nanowires, and we're looking at the top of them. These are processed such that they have a p-doped center region and then an n-doped ring around that with a hexagonal structure. You can nicely see it in this high resolution scan here. So also from top surface, this can work nicely. And then of course we can correlate the electrical information to the topography information. Just the last example on the electrical modes is a popular mode or property to measure the surface potential, or related to that, the work function. It's of interest for two reasons. One is to measure the work function that actually can again be linked to the carrier concentration of your sample, or to measure the potential distribution on an operating active device. And that's the two examples I have here. These are two devices. One is a semiconductor nanowire, and one is a gap here with two metal contacts. And we're interested in measuring with nanoscale resolution the potential distribution while we apply voltages between the different contacts here. So we can nicely see that here. This color scale is a little bit chosen on purpose to show the equipotential lines. And we can see that there's a strong electric field between the plugs, between the two metal contacts as expected, lower field here. And we can actually see that that field is stronger toward the right side as it is to the left side. And that can be of relevance for when we're making devices. On the nanowire as well, we can see how the potential varies from one contact to the other as we're applying a voltage between the two contacts. But also along the nanowire, we can see, for example, here there's a little bit of a jump in the potential profile that indicates that there's actually a defect in that wire that was not expected. I'll just show one of the other properties, which is the thermal measurement capability. Here it's on a laser, an edge-emitting laser structure. So again, cross-sectioned. The laser is active. Here we can see in the topography, we can see some of the areas that define the active area. And the laser is basically emitting out of the surface of the slide here towards us. And when we use a special tip that actually has a small thermistor built into it, you can see this AFM tip now has two contacts here, and in between the two contacts is a small thermistor. If that scans the surface and the temperature of the surface is changing, the resistance of this will change of this tip, and we can easily monitor that with like a Wheatstone bridge and then quantify that into a temperature map. That's what we're doing here. So at the same time as the topography, we're getting a heat map of the active device, which obviously allows us to detect where the hot spot is, basically where the laser is emitting, as well as at the heat sink, see if the heat sink towards the substrate, if that is efficient. If it's not heating up, it stays dark low. And then we can increase the power of that laser, which is a typical experiment to do when we work on active devices like this. Increase the power and then observe how that temperature variation between the substrate and the emitting area is varying, basically to characterize the device with nanoscale resolution at different locations. So I'll keep it to this as an introduction and hand it over to Chen. I'd just like to point out that for us, being a company that develops and also sells these AFM instruments and techniques, it's very important to have these industry academic collaborations. This is how we interacted with the University of Cambridge, actually over a number of years with a group of Professor Rachel Oliver. Typically, we are good at developing new characterization methods, but we're very limited on actual relevant case studies, and that maybe even also on the methodical experimentation that comes with those. And in a lot of the universities, and in particular the University of Cambridge, we found a great partner in some of these applications that we can ensure that we're developing the right thing. We can ensure that we optimize some of these modes for the ultimate performance that make them interesting. So with that said, I'd like to pass it to Chen, who's going to talk to us a little bit more about that electrical characterization.
Great. Yeah, great. And thank you for the excellent talk, Peter, and also thank you for the kind introduction, Alex. And also would like to thank you all for attending this webinar. So good afternoon. So my name is Chen Chen, and I'm a PhD student supervised by Professor Rachel Oliver at the University of Cambridge. So I'm happy to share that recently I passed my Viva. Yeah. And yes, so today I'm going to present this work scanning capacitance microscopy of nitride high electromobility transistors. So this work was done in collaboration with Bruker. So people kindly offered a lot of technical support. And also, personally, I'm quite grateful to have the opportunity to work with Peter and his colleague Steven long time ago. Then for this work, so mainly Peter, my supervisor Rachel, and also my mentor Rishi, and also me, we together developed the core technical details of this application. And of course, I'm also grateful for other colleagues for their help. So together, we published a paper based on this application, and it was published in the journal Applied Physics Letter, and this paper was highlighted as editor's pick. So I'm going to talk this application in more detail. So first of all, let's talk about nitride high electromobility transistors, HEMTs. So HEMTs can be used for many important applications like power switching and also radio frequency applications, RF. So here is a schematic of a typical HEMT transistor device. So as you can see, it mainly consists of two nitride layers. The first layer is the top aluminum gallium nitride barrier layer. Below it is a gallium nitride channel layer. Then because of the spontaneous and also piezoelectric polarization difference between these two layers, so you can imagine there will be a two-dimensional electron gas at the interface. So for this 2-DAG, it's featured with high sheet carrier density and also high carrier mobility. Then after the wafer epitaxy, we can add metal contacts, source contact, gate contact, and also drain contact. Then if we don't apply any voltage to the gate, then you can imagine the 2-DAG below is on, so that current can flow freely. Then in another case, if we apply a negative bias to the gate, then the 2-DAG below the gate can be depleted and hence no current can flow. So this is a basic principle of HEMT. And so ideally, HEMT structure looks like this. It looks perfect, but in reality, we are worried about many real issues. For example, impact of surface defects, for example, dislocation-related defects, and also subsurface features like thickness inhomogeneity and also aluminum content inhomogeneity. So we are curious what could be their impact on the electrical properties of 2-DAG. So here I can give you a real example of the sample surface of one of our samples. So as you can see, the sample surface is covered with fissures. So fissures are a kind of dislocation-related defects. They are commonly seen on the surface of a HEMT structure. So in this work, we are going to investigate what could be the impact of fissures on our 2-DAG. So these days, especially for the radio frequency application, the gate region of a HEMT device is shrinks down to smaller than 100 nanometer to enable ultra fast switching function. Then we can imagine in reality, let's say we have a piece of gallium nitride HEMT structure wafer. You can imagine the threshold voltage, it may not be necessarily always consistent across the whole wafer. And if that's true, then we can imagine that produced HEMT device from the same piece of wafer will have different electrical properties. That's why it's quite important to characterize threshold voltage of gallium nitride-based HEMT structures at a nanoscale. And this is a topic that we are going to dive in today. And as we may know, so there's already a quite conventional AFM-based technique that can characterize semiconductors' electrical properties across the whole surface at a nanoscale. So it's called conventional scanning capacitance microscopy, SCM. So Peter mentioned in his talk previously. So I can give you more details. So SCM can characterize the carrier concentration and type near the surface of semiconductor. So this is function. Then how does it work? So here, this is a schematic of SCM. So as you can see, there's a conductive tip scan a piece of semiconductor with an oxide layer on its surface in contact mode. Then if we apply an AC bias to the circuit, then you can imagine the electrons below the conductor tip can be either depleted or accumulated. And also note that these three together form a MOS capacitor. Then because of the depletion and attraction of the electron layer, you can imagine the capacitance value of this local MOS capacitor can change. So here I give you an example of the CV curve of an N-type semiconductor material. So please note, in reality, in SCM, the conductor tip is grounded and the sample itself is biased. And hence in this presentation, all the bias I'm talking about are sample bias. So let's go back to our N-type semiconductor material as an example. So to enable carrier depletion and accumulation, we need to add a AC bias. So here we add an AC bias. Then for lightly doped semiconductor region, you can imagine because it's lightly doped and hence the electrons below the tip can be more easily depleted, and hence the capacitance change delta C will be bigger. This reflected as a difference in dc divided by dV amplitude. So based on the dc divided by dV amplitude value, you can judge whether it's highly doped or lightly doped. And also for a piece of p-type semiconductor material, the CV curve is just a mirror image of that of n-type material. So you can imagine the sign of the slope is opposite. So then based on the sign of the slope, you can tell whether it's n-type doped or p-type doped. There's another mode called scanning capacitance spectroscopy, SCS. So basically, you can record a local dc divided by dV curve using SCS mode. And how does it work? Again, we use the CV curve of our n-type semiconductor material as an example. Then for this CV curve at a certain DC bias, we add an additional certain AC bias, so delta V. Then it will cause a local capacitance change, delta C. Then together, at this DC bias value, we can get a local DC divided by dVV value. So you get a local data point at the X value and Y value. Then we can imagine if we apply an AC bias and this AC bias swaps the whole range of the DC bias, then eventually we will get a local DC divided by dVV curve. Then let's go back to our original target. So we like to characterize our gallium nitride based hand structure. So in comparison with bulk doped semiconductor, so for our hand structure, it has a highly concentrated or highly well-defined carrier layer 2-deck below the conductor tip. And because of its high sheet carrier density, AC bias alone is not enough. So we need to add additional DC bias to deplete the 2-deck, and hence we can get conventional SCM signals. And for this work, the task is more challenging. So we not only want to get the SCM contrast, but also we want to map the threshold voltage distribution. And for the conventional SCM itself, unfortunately, it only maps at a fixed DC bias, so there's no access to threshold voltage. Then in our SCS mode, yes, indeed, we can get a local DC divided by dVV curve, and it's helpful to deduce a local threshold voltage value, but it's quite impractical to do so at every pixel. That's why we are going to talk about a new technique called hyperspectral SEM. So in hyperspectral SEM, so first we approach the tip to the sample surface. Once the tip engages on the surface, it will hold on the sample surface. And during the holding period, an AC bias swaps swaps a range of increasing bias, so that during that hold segment, you can collect a local DC divided by dV curve at that pixel. Once it's finished, we withdraw the tip and move to the next pixel, and repeating the same process. So eventually, hyperspectral SEM can automatically collect local DC divided by dV spectrum at every pixel. So it's quite promising for mapping threshold voltage. And also it overcomes limitations of both conventional SEM and SCS. So in this work, so we are going to test this technique to map threshold voltage of our hand structure. So first, let's have a look at our sample. So this is a high-resolution topography image of our sample surface collected using a sharp tip. So as you can see, there are a lot of fissures on the surface. Then the question arises, what's the impact of these fissures on local threshold voltage? So we are going to use additional technique, conventional SEM and also hyperspectral SEM to investigate into that. And as a general note for electrical AFM, there's a dilemma that you may expect. So if you want to get strong electrical signals, the tip is normally expected to be blunt, but it will sacrifice a high-resolution topography image, and also vice versa. Then in this work, we used a new technique called multi-microscopy technique. So for this technique, we first use a sharp tip to collect a high-resolution topography image at our target region. Then we shift to a blunt conductive tip and scan the exact same area to further collect electrical signals. So here, these white arrows highlighted the broad features, and based on these broad features, we are quite confident we exactly scanned the same area. Then here I select two regions for initial study. One is a fissure region labeled as F, and another is a non-fissure region labeled as N. So I'm going to investigate what is their local DC divided by dV curve look like. So we collected local DC divided by dV curves in two modes, SCS mode and also hyperspectral SEM mode. So as you can see, in both cases, the fissure always shifts towards to negative DC bias in relative to the non-fissure curve. So the relation between these two spectrums captured on the fissure and the non-fissure region is consistent in both modes. And also, if we have a further look, here I highlighted two DC bias value on the two shoulders of the peaks. In both cases, you can see, for example, at this bias, the fissure shows a bigger DC divided by dV amplitude value than the non-fissure region, and the situation is just opposite when the DC bias increases. So we expect we may see contrast between fissure region and the non-fissure region if we scan at these two DC bias values. And indeed, so we did a scan, and here in the conventional SEM mode, we can see at the lower DC bias 2.6 volt, the fissures show bright contrast. Then when the DC bias value increases to 3.8 volt, then there's contrast inversion. So fissures show opposite dark contrast. And also we scan the same area using hyperspectral SEM mode. So here I plotted the local DC divided by dV amplitude slice from the hyperspectral SEM dataset. So when we did the hyperspectral SEM measurement, there were about 128 multiplying 128 pixels in this 1 micrometer multiplying 1 micrometer target area. Then for each pixel, there's a local DC divided by dV V curve. Then here I say for each curve at each pixel, I like to collect the local DC divided by dV amplitude value at this 2.5 volt. Then eventually I can get a complete map or a complete DC divided by dV amplitude slice exactly at this DC bias value. And as you can see, the features show bright contrast. Then similarly, we collected a slice at a higher DC bias, 4.6 volt, and the features show a dark contrast. So you can see the contrast in both modes is consistent at both lower and also higher DC biases. So overall, we can see that hyperspectral SEM data are quite reliable. Then based on that, we are going to extract a nanoscale threshold voltage map from our hyperspectral SEM dataset. So here is a calculated threshold voltage map. And how did we get that? So for each pixel, or at each pixel, we have a local DC divided by dV V curve. Then we define, so we fit the curve. And after fitting, we define the peak position as our local threshold voltage. We extract it and plot it into the figure. And of course, I can't do it manually. So this calculation was done by using hyperspectral hyperspy script. Then after we get in this nice threshold voltage map, so we are going to further dive deep into it. And thanks to our multi-microscopy technique, now we can directly correlate our threshold voltage map with our high-resolution local topography image. Then what's the impact of, for example, fissures and other features? So first, let's check the impact of fissures on local threshold voltage. So as you can see, for these highlighted fissure regions, their contrast is not consistent, which suggests fissures show varying threshold voltage. And also, for most of fissures, they show a darker contrast, which suggests most of fissures' threshold voltage is smaller than the average threshold voltage of the whole area. For example, for this local fissure, its local threshold voltage value is 3.44 volt, which is smaller than the average threshold voltage, which is 3.7 volt. Then what could be the reason that most of the fissures reduce the local threshold voltage? One of the potential reasons is that fissure formation is linked to threading dislocations. That is a fact. And for this threading dislocation linked fissures, impurity segregation could happen to the cause of the dislocations, and hence makes the dislocation negatively charged, and hence local two-deck is depleted, and hence we have a lower local threshold voltage value. And also let's check the non-fissure regions. So here I highlighted two big pieces of non-fissure regions as an example. You can see the contrasts in this area are not consistent, which suggests there's also some threshold voltage variation in non-fissure regions. And for this threshold voltage variation, potential reason could be the thickness or aluminum content in homogeneity in the argon barrier layer. And again, I'm going to pick up two examples. So non-fissure region N1 and non-fissure region N2. So I collected their threshold voltage value. The difference is roughly about 0.2 volt. And for this quantitative threshold voltage map, another advantage is that based on the local threshold voltage difference, you can also quantitatively calculate how big is the thickness in homogeneity, and also how big is aluminum content in homogeneity. Then in our case, for this sample, 0.2 volt threshold volt difference could be caused by a thickness in homogeneity of about 0.8 nanometer, or aluminum content in homogeneity of 0.05. So, or a combination of both. So it's quite powerful. And yes, then we can see that both fissures and bearing homogeneities could be obstacles to a uniform and reproducible threshold voltage distribution. Then let's have a quick summary of this presentation. So first, we successfully applied hyperspectral SEM to characterize gallium nitride-based HAMT structure to map threshold voltage distribution quantitatively and also at a nanoscale. Then also we get deep insights which can't be provided by conventional SEM. So insights like identification of the threshold voltage variation among fissures, and also we can quantitatively calculate the subsurface layer inhomogeneities. And also we successfully used the multi-microscopy approach to overcome the typical trade-off between high resolution topography and also strong electrical signals. And also hence it enables us to correlate nanoscale features to local threshold voltage directly. Then for our sample fish, we found that both fissures and argon bearing homogeneity can alter local threshold voltage distribution. In detail, we found that most of the fissures, they can reduce local threshold voltage value, and also the thickness or aluminum content in homogeneity can cause threshold voltage variation in non-fissure regions. And hyperspectral SEM enables quantitative calculations of these above-mentioned inhomogeneities. So to summarize my presentation, so we find that overall SEM is indeed a very powerful technique to help us explore structure property relationships in HAMT structures. Yeah, thank you so much for your attention, and I'm happy to answer your questions and comments. Thanks.
Great. Thanks very much, Chen. Thanks, Peter. I'm just going to spotlight you both now for the question and answer section. So yeah, if anybody does have any questions that they want to ask, feel free to pop them into the Q&A. We've had one come in from Aisha, so this is for Peter. Aisha was wondering if Bruker has an AFM system for in situ observation of electrochemical processes, for example, real-time observation of surface evolution of grains in electrodeposited polycrystalline metallic films.
Yeah, there's several ways of doing in situ electrochemical work. So in situ, I mean AFM work inside an electrochemical cell. It depends a bit on the AFM model, what type of cell is available and what type of work one can do. But some of the most basic work that we do in electrochemical environments is topography imaging, but then in the electrochemical conditions. But there's also a possibility to make the tip more than an imager of topography in the electrochemical environment. It could also become an active electrode where the tip is doing either electrochemical reading or contributing to the electrochemical process. So popular in things like battery, fuel cells, corrosion studies, for sure, and possible. Yeah. But some of the modes, like the scanning capacitance things that were discussed in detail here, are not yet done or not possible in electrochemical environments.
Thanks, Peter. We've had another one come in asking, what do you consider the most consistent and recommended method for preparing cross-sectional samples for electrical AFM? Is it manual cleaving, FIB, or something else?
out of personal experience, it really depends on the sample you're dealing with first. If this sample is like a process device and has metal lines on it, cleaving might become a lot more difficult, and you might have to do a polishing method or use one of the precision cleavage instruments that exist, maybe combined with cryo, because you have to deal with the different material properties between the metal and your semiconductor layers. If there's no metal layers, and it's most of the compound semiconductors will cleave relatively well. Of course, need to gain some experience in doing a proper cleave. And I would cleave those because cleaved surfaces are typically or can more easily be of higher quality in terms of surface state and roughness and surface charges. But if it's silicon-based, so not compound, but if it's silicon-based, often polishing is working pretty well. Some groups use focused ion beam to prepare samples, but you have to be very careful with that because the ion beam will implant into your area that you're actually interested in. So you have to work with low doses, or sometimes you need to follow your FIP step with a very short polishing step to remove that amorphized layer or modified layer that the FIP left behind. Yeah, maybe a little bit of a long answer and not a single preferred method there. It's almost like you need a recipe book about different recipes for different types of samples.
Yeah, and following Peter's comments, I'm also happy to share my experience when I was preparing a cross-sectional sample for electro AFM. Because in my thesis, I also did some cross-sectional characterization. So for our sample, it's quite critical to achieve a smooth cross-section. And how did I do that? It sounds quite incredible. So you need a hammer and also a diamond square. Yeah, it sounds incredible, but later I will explain the credible scientific principle behind it. So it's my case, may not work for your sample. So first I'm going to give you some detail what's our sample about. So it's gallium nitride grow-arm silicon. So for both gallium nitride and also the silicon, they are monocrystalline. So I suggest if you want to use my method, make sure your sample is monocrystalline. Then how to use my incredible method to cleave the sample? Simple. You should put. Okay, I have a paper. Let's say this is our wafer and this is our diamond scribe. Put your diamond scribe at the edge of your wafer perpendicular, and suddenly use hammer to smash the diamond scribe. Yeah, although the diamond scribe will be dead, but you will get a nice cleave starting from the hitting point. And in our case, we find that the cross section of the relieved, the crystal plane of the relieved cross section is always M plane of gallium nitride. Then we are thinking, what's the scientific reason behind that? So in my thesis, I suggest when we smash the hammer, there will be a very big and sharp force or strain accumulating in the hitting point, and it needs to be released. And to release that, it will naturally follow the natural crystal plane of our gallium nitride. That's why we always get a cross section which is M plane. So to summarize, if you want to use my method, your sample should be monocrystalline. And how to use my method, you need a diamond scribe and hammer, just hit it, and also pay attention. You need lab goggles, don't forget, and also better do it in film cardboard. Yeah, and try it. If it works, let me know.
Sounds interesting. I have a couple of questions. So what is the applicability of the hyperspectral SCM technique to other wide bandgap materials and also other types of devices, so non-hemped structures?
I think that's a question for you, Chen.
Yeah, it might be more, Chen.
Sorry, could you please repeat again?
Sure. So what is the applicability of hyperspectral SCM to other wide bandgap materials, so not GaN, and also other types of electronic devices, so not hemped?
Yeah. So you asked whether hyperspectral SCM can have powerful applications for other samples, for example, non-gallium nitride samples. Yeah, I think you can definitely use the same technique to characterize, for example, threshold distribution of other HAMs made of other materials, for example, gallium arsenide based or phosphor-indium based. Yeah, it's quite straightforward. And for me, I personally believe hyperspectral SCM is quite powerful because you will get a 3D data cube. By 3D data cube, I mean, first, let's say we have a 2D plane. This is our sample surface. And in each pixel, you will get a local dc divided by dVV curve. That's why I call it 3D. So it's a 3D data set. And from this 3D data set, I'm very sure you will get a lot of information. It depends on your sample and also depends on your applications. To name one example, let's say, I've already mentioned the concept of dc divided by dV amplitude slice at a certain dc bias value. Let's say if we collect all the slices together, then you change the dc bias, you will see the like animation, for example, how the SCM signal changes along different dc bias. And in that case, for example, for our transistors, you may identify at which dc bias there's a failure on the transistor surface. Does that make sense?
Mm-hmm.
Yeah, you can show the animation, and at a certain dc bias, voila, you see there's a local abrupt change of SVM signal, and this may be a good indicator of the device failure or other possible phenomena. Yeah, so I think hyperspectral SCM is quite new to the community, and I encourage people to try it. And if you have questions, Peter is the expert, and I can also help if you need.
Great, thanks, Chen. One final one. This one's probably more for you, Peter. So I know you said that when you're collaborating with universities, you like having these kinds of case studies for almost sort of representing how you can use the characterization techniques and the instrumentation that Bruker is developing. Is there a specific type of case study that is like most valuable or beneficial for Bruker when collaborating with universities, or is it a kind of a case by case?
I think today the AFM is used in so many different application segments or market segments that it's hard to pin down a single or a few that are of interest. There's so many of interest. For us, it's often hard to get access to relevant samples, and relevant can mean both from an academic point of view and or from an industrial point of view. So if in a collaboration, that we always look for that. If there's a availability of an interesting and relevant problem, and availability of samples that go with it that allow to test and explore various approaches. Of course, the higher impact things are those that are still novel, so there's still a lot to learn, but where there's a strong interest. So to name a few things now, quantum computing related, maybe machine learning, and this maybe moves us more from the interpretation and the analysis side towards that rather than the data acquisition side. But that's also of interest. And then the correlation of properties, because we, on various materials, we more and more we're facing material characterization challenges where we're not just interested in the electrical property, because that is not giving all the answers. We want to know the electrical, mechanical, thermal, chemical, nanoscale property. And then based on all of that information collected, come up to a better understanding of the samples we're dealing with. So that correlation study is another high field of interest. And then to name one more, anything that is related to green energy, could be photovoltaic, could be perovskites, could be fuel cells, battery. That is also a good topic.
Great. Cool. Thanks both. We've already run over time, so I'm going to close everything there. So thank you to both our speakers. Really, really interesting. Hopefully the attendees have also found it valuable. I'm just going to put a couple of things in the chat for future reference. So we've got another webinar coming up next month, so details are on there as well. And we've got REWIRE's annual showcase coming up at the 18th of November, which we are keen for people to attend. So yeah, details are there. But yeah, thanks again, everyone, for attending, and for our speakers for participating, and enjoy the rest of your day.
Yeah, thank you.
Thank you. Bye.
Bye-bye.